let's kick it off with the introduction to machine learning. On the next few slides, we're going to have a look at how machine learning differs from traditional rule-based programming. So what we have here on the top of the slide is a traditional rule-based programming approach, where on the input side we have data and a set of hard-coded rules, and those rules would generally be formulated by domain experts. And then we can take the rules and apply them to existing data set to generate some answers or a summary of what's in the data. And this is not new. In fact, people were doing this for many, many years. And what we have here is a quote from Arthur Samuel, who was an IBM researcher. And he was living in this world where already traditional rule-based programming existed. And he found it quite cumbersome to come up with all these hard-coded rules. So he was envisioning a world where computers would learn from experience rather than having to be explicitly programmed to perform a certain task, which in this case was applying the rules. So how does this domain shift then lead to the emergence of machine learning? Well, we have data on one side, and now instead of having the domain expert create the rules, we have a machine learning algorithm, a mathematical construct that helps us find these rules. And when we apply the algorithm to the data, what comes out is a learned model. And then this model applies the rules to a new and unseen set of data. So it actually generalizes beyond the data that it's seen as input. And with that, we can now generate answers, or we also call them predictions. Another way to think about machine learning would be the quote that we have here from Tom Mitchell, where he's saying a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at tasks in T, as measured through the performance P, improves with experience E. So this very much captures the same nature of things, where we have some sort of performance evaluation E, we have a certain task that we want the machine to learn. That could be classifying things or translating text. And by providing experience, by providing sample data points, eventually we would hope that the computer would learn from those sample data points and come up with a good model. So the important ingredients really to machine learning are therefore data, and then on the other side, the algorithm, or the task that we want to perform. So we're going to have a look at both of these things, and we're going to start with data, also called features, first. So features, they're usually denoted as lowercase x if we're referring to a single feature, or uppercase x if we're talking about a collection of features. And very simply put, you can think about features as a table of content where every column refers to a particular attribute. What we have here is an example tabular dataset, where the first column refers to experience in years, second column is age bracket, and then the third column is gender in this example. So as we can see, every row here would describe one individual person, and the columns are the various attributes. And in the case of a tabular dataset, we can see that the raw values inside the table are either strings or numbers, so both are possible. And this would be a typical tabular dataset. Usually, if we want to differentiate between the individual features, we would put a little subscript with the number of the column that we want to refer to. So now we have x subscript 1 for the first column and x subscript 2 for the second column. And as you can imagine, there could be arbitrary many attributes, so we can just keep counting as we go. Obviously, tabular data is not the only data format. We could also be working with image data. In the case of image data, the raw values are actually the light intensities in the individual pixels. So when working with images, we actually need to break it down into the pixel values and restructure that image to actually end up working with it, but it's certainly possible to do nowadays. We have the computational power, we have enough storage and machines that are powerful enough to actually work with image data as well. So what you're seeing here is just a screenshot of an example image data set, where you would usually have a folder with all the images that you want to learn something from. What would be an image task that we could learn? Well, we could classify what's on the image, or we could detect different scenes or objects on the image. Those are just examples. Obviously, there are many more different computer vision or image-related tasks as well. So if we can work with images, you might be wondering, can we also work with language? And the answer is yes, we certainly can. So now we have an example language data set here. This is an example of a translation task where you would have a source language and then a target language that you want to translate into. And here you can see we're trying to learn how to translate from English to German. And there could be additional annotations or tags associated depending on what kind of information you want to translate or whether you want to pay particular attention to how the translation should work. So in the case of language data then, the raw values are now going to be strings, text snippets, words, paragraphs, or whole documents could be considered one source that we want to translate. And if we have all of these different data types, the question then usually becomes, well, can we combine them? And yes, certainly that's also possible. That would be called multimodal data, and that's just a combination of everything that we've seen so far. A special type of feature is the so-called label or the label column. And labels are usually denoted as lowercase y. And the labels are usually the answer that we want to generate using a trained model. So the whole point of providing data to an algorithm and learning the model is usually to predict a certain target, a certain outcome, something that we're interested in. And we need historical labels or information of what the connection between the features and the labels is to ultimately learn those rules. There is a bit of a caveat where labels are not always provided, so one of two ways this could go. Either we go out and label the data that we already have, or we perform a completely different type of machine learning that actually works without labels, which is something that we'll look at a little bit later in this lecture as well. So in the case where we do have labels available, we need to distinguish further between numerical and categorical labels. Numerical labels will be labels where we're trying to predict a continuous numerical value, such as insurance price prediction. In the case of categorical, as the name suggests, we are trying to predict different categories. Those can either be binary, yes or no, or it could be multiple classes, such as would be the case for disease type prediction. And now we're going to move on to a machine learning algorithm example. So again, to remind you, the two key ingredients to a machine learning model are on one side the data and then on the other side the algorithm. And the algorithm example that we have here is we want to generate a prediction that is a weighted combination of the features that we have. And to make this a bit more concrete, let's say our goal is to predict a healthcare score that could then be used to set the insurance price of any given individual. And we're going to introduce a little bit of mathematical notation now, where you would see on the left-hand side now we have y hat. So this indicates now that this is going to be a prediction that we're going to make. And y hat is a function of x, of the features that we have in our data set. And we said we're going to use a weighted combination of our features. So we have the addition of all the individual features multiplied each feature with individual weight components. So the features here in this equation are going to be our measurable pieces of information, and those generally need to be in numerical representation. So that means even if we have text values or maybe categorical entries in our table, we first need to convert it into a numerical format. And we're going to look at that when we get to the data prep and data processing before the model train stage. So this is just to let you know that if you do have a feature that is maybe categorical or a text value, we do need to convert that into a numerical format first. And we'll see an example of that in just a moment. So let's just say feature x1 corresponds to the number of hospital admissions for any given individual. So we would have a historical record of different individuals that would have potentially different number of hospital admissions. And now we're going to look at one particular example where x1 is equal to 5. So if we wanted to make a prediction, this is now going to be an unseen and new patient, and we're going to predict what is the health score for that particular individual. And we ask them how many times have you been admitted to the hospital in the last X years. Well then, if they give us the answer 5, we can use that and plug it into our equation that we have at the top. So obviously there's still quite a few missing pieces. First of all, we need to figure out what these W values are. The X, we can just go and ask the patient that's coming in. The W's, well, those are actually being learned during what is called the model training stage. And that uses the historical records where we have our table of X, our features, and the corresponding outcomes from other patients where we already know what the healthcare score is. And we can use those to learn the relationship between X and Y. And that gives us ultimately the weights, which determines how much influence a given feature has on the output or the prediction. These weights, they're also called model parameters in a parametric model, and as I just mentioned, they're being learned during the model training stage. So we don't have those W's up front, we actually need to learn them by looking at many data examples. And this is what the learning in machine learning is all about, where we look at many examples, we look at the features, we look at the labels if we have access to them, and then we find out what those W's are. And there are going to be different techniques on how to find those W's. We're going to look at one of them, but just to let you know that there are many different methods on how you can actually find those W's. So let's say we performed the training, we looked at all the historical records, and we found that W1, the weight for the number of hospital admissions, is indeed a very high positive number. W1 was found to be 100. We ask our patient, the individual again, what is your lifestyle look like? Do you have a healthy lifestyle? Yes or no? And now you're going to see one example of this categorical answer, yes or no. That's not intrinsically a numerical value, but we can easily represent it as ones and zeros. And there exist methods to do that if you have many more categories as well. For now, we just have a yes-no answer, so we can easily convert that into 1 and 0. So this particular person is indicating that yes, they do have a healthy lifestyle. And again, we already have learned in this example what the W values are. And it so happens that the value for W4, weight for healthy lifestyle, is a medium-large number, but keep in mind here, this is now going to have a negative sign. So these weights, these W's, they can be positive or negative, they can be very large or very small. So what this would mean then is for our prediction, the healthcare score would actually be brought down if somebody has a healthy lifestyle. So that is something good. So if we think about insurance price maybe going up with depending on how high the score is, if somebody indicates that they do have a healthy lifestyle, well, that would bring the score or the price down. And for now, we're going to stop here with the example. Obviously, there would be many more features about the individual that we could ask them, like their age or maybe other history that they have. And as I said, we would have learned the W's from looking at historical examples. For now, we're just going to leave it as is, so you can see what the predicted score would be. So we have base value 200, that is the offset. We'll see that again in just a moment. And then 100, that was the weight for our first feature, times 5, because that is how many hospital admissions the individual indicated that they had in the recent years. And then minus 25, that was the X4 weight, so W4 was minus 25. And they did have a healthy lifestyle, yes, so we multiply by 1. And what we get is 675, plus minus an error term, because obviously we didn't consider all the features now. And in any case, we do need to keep in mind that these predictions, they always come with a certain error associated to them as well. And this equation that we looked at in this example is actually a very famous one. It's the so-called linear regression, and it's the building block and very essential to all of machine learning. So even when you start talking about more advanced models like neural networks, they actually are composed of many linear regressions put together in very advanced ways to make and build a full neural network. So let's come back to the different types of machine learning. And we already actually introduced the key factor that distinguishes between the different families of machine learning or the different types of machine learning, because it all comes down ultimately to the labels. So if the data is indeed coming with labels, either numerical or categorical, then we say it's supervised machine learning. And the model learns by looking at the examples, the features in combination with the labels. So this is supervised machine learning. On the other hand, if we only have X collection of feature available and there are no labels, well then this constitutes unsupervised machine learning. And here the goal or the idea is to find patterns or similarities in the data that we do have access to. So there's not going to be an external label. It's just about finding patterns, commonalities, and similar characteristics in the data sets that we have. And as we said earlier, the labels, if we do have them, they can either be numerical or categorical values. And that then forms, again, a split between what is called regression and classification in the case of supervised learning. And in the unsupervised case, obviously we don't have any labels. So one example of a type of learning net would be the so-called clustering algorithms, or clustering as a problem type. And on this slide, you also have examples of what each of those would be. So for regression, let's say it's a insurance price prediction that we want to conduct. For classification, it could be a disease type prediction. And for clustering, where it's about finding similarities and similar characteristics, it could be something like skill and experience grouping in a hiring or admission scenario. And each of these different problem types now comes with a whole list of algorithms that we can use to solve or tackle that problem. We already had a look at linear regression as one machine learning algorithm example for regression, but there exist many more. So you can see the list here. We have k-nearest neighbors, neural nets, decision trees. In the case of classification, it's support vector machines. And again, you would actually see some repetition here. K-nearest neighbors, neural nets, and decision trees, because some of these different algorithms, you can modify them slightly and either make them predict a continuous numerical value, or you can make them predict a class or a category. What you should also notice though is then when we look at clustering, there is a completely different list now of algorithms. We have principal component analysis, or PCA, collaborative filtering, or k-means clustering. So as you can see here, there's a long list of algorithms, and in fact there are many more. So if you were to look up regression, classification, or clustering algorithms, you would find a very, very long list of algorithms nowadays. And what we're going to have a look at now is a deeper dive at each of the different problem types, and we're going to start with regression. In fact, this is the one that we already looked at in our machine learning algorithm example, and this is just a visual and a table again. So in the bottom right corner, you have an example data set where we've also highlighted the label, the healthcare score, the thing that we want to learn how to predict. And then we have a set of features that describe the different individuals, like the age, BMI, smoker, and ethnicity. In the top, you have a visualization of one feature, X1H, versus the healthcare score. Obviously, you could add more features as well, but then it becomes difficult to visualize. The reason why we have this chart there is just to illustrate how to generate a prediction. In the case of regression, it would be the line of best fit. So everything on the orange line, those are predicted values. And if you have a new patient or a new individual coming in, you have a certain age for them, you just ask them for their age, you can just look up corresponding to their age, what is the respective healthcare score, and then that would be your prediction. In the case of classification now, we once again have a line, but this line is a different line now because that's actually a decision boundary which is separating the different outcomes. In this case here, positive and negative outcomes, yeses or nos, approved or not approved. So this line that you see here is actually a separation, a boundary between the two different predicted classes. And once again, we have an example data set here, the labels plus and minus, approved and not approved, and then it could be a similar set of features. So you can see here the difference between the classification and regression case is really just what the label is all about. And the final example that we have now is the clustering example. And you should note now that on the data table, there is no indication of any label whatsoever. We only have the features. And now we're plotting two features, age versus BMI. And visually you can already see that there are certain groups emerging. There is a cluster, which also eventually leads to the name clustering, of data points that are more closely together than the other data points. So I would argue that in this particular example we can see 3 clusters, one in the top left, one center bottom, and one to the right. And one algorithm example that could help us find those clusters programmatically, especially when it comes to having more dimensions. So now we can do it because it's a 2D plot and we can look at it. But keep in mind that usually you would have 50, 100, maybe hundreds of features, and then you cannot visualize what's going on anymore. So you need the help of an algorithm to eventually find these clusters. So one kind of algorithm that could help us with that task would be k-means clustering, and we can have a look at the outcomes that k-means would produce. And in fact, it is confirming the hypothesis that we had from visually looking at it. Indeed, there are 3 clusters to be found in this particular data set. Little caveat here, the k in k-means actually stands for how many clusters we want to have as an output. So we can actually tune how many clusters we want. If I'd set k to 5, well then k-means would find the 5 groups in that particular data set. So finding the correct k is actually a bit of art and science on its own, and we can have a look at that later on as well.